Okay guys, this is 14B lectures. After reading this, you should be able to identify major sources of oil pollution as well as some ways to remediate oil pollution. And at the end of it, we're also going to look at various other types of pollution. Okay, and I'll show you some kind of cool things some of your classmates did for y'all, so you can learn from it and take from it as well. All right. Okay, there are several types of oil pollution. Petroleum products are highly toxic to many marine organisms, including birds. It gets on them. It's very hard to get off. You have to take it off manually, right? There's really not a good way to just have a very efficient way to do it. You have to pick them up one by one and use some sort of dispersing agent to clean them, like soap or something like that. Mammals, fish, algae obviously is very affected, especially ones that are surface algae, ones that float on top, and microorganisms that form the base of the aquatic food chain. When this stuff sinks to the bottom, it messes up everything on the floor. One source of oil in the ocean comes from drilling. So you need to know that there are three ways that the oil is going to get into the ocean. The first way is from drilling from offshore platforms, and there's a video in the 14B part of the playlist in pollution where you can just see, like, when they're capping a drill site, that there is some oil that just seeps out because of density and things like that. It just comes up in pressure. The second way is that it's going to come from tankers like the Exxon Valdez, right? And we studied about that. And of course, it also occurs naturally, right? There are cracks and fissures in the ground. The stuff on the seafloor that is that's depositing onto the seafloor that will one day become fossil fuels, while it's becoming that and decomposing in anaerobic conditions, will have some kind of toxic chemicals. Right? So this happens naturally, though. Okay, so those are our three ways. You need to know that. Okay, oil pollution, you need to take a good look at this and just make sure here are the sources, right? And this is U.S. versus the world, U.S. versus worldwide. So let's take a look at the U.S. Make sure you commit this pie graph to memory, at least to kind of generally know the breakdown. So natural seeps, we have a lot of natural seepage here. Okay, let's look over at worldwide. Okay, so it's kind of cool to kind of keep that in context, right? All right, there are ways to remediate oil pollution. I would definitely recommend watching those videos because it's a lot easier to remember the techniques by watching it rather than just reading and trying to memorize, right? Okay, so containment, they use booms to keep floating oil from spreading. You can also use basically big plastic barriers and things like that. Some people try to use like nets, but obviously nets, it's oil, so it's going to get through a lot of it unless you come up with some material that's going to stick to the oil very well, right? Okay, then they take vacuums and they'll suck up as much as possible. But you saw in the case studies for Exxon Valdez that there were fishermen that were using just buckets that were more efficient than some of the vacuums, right? So you have to use a pretty good, I would say you'd have to use a pretty good chemical coagulant or something like that to kind of make it stick and clump together a lot better. So the chemicals right here will break up the oil and make it disperse before it hits the shoreline. And a lot of times this will settle out if it breaks up. If you use it in conjunction with coagulants, it'll settle out to the bottom of the floor. You know how sediment works. And it might look very clean in the top parts of the ocean, right, where people will hang out and swim, but the seafloor can be damaged, right? So you also have to clean up the bottom of the seafloor if you're going to do things like this. Okay? And then we can use bacteria. There's certain forms of bacteria that will process this and make it into things that are not as chemically damaging to the surroundings. We can do this by genetically modifying bacteria, but this process is expensive and there aren't very many of these things around, right? So this is something that we're looking at for the future, but you also have to take into consideration trophic pyramids. What's going to happen when this bacteria moves up the food chain? Bioaccumulation. What is the effect of this bacteria going to have on the entire ecosystem? Because if these guys can persist in highly toxic areas, they have an overlap. They have less overlap with their competitors, right? So remember, if we look at survivorship curves and we look at things like this, so the regular bacteria might be able to live within a range of toxicity maybe here, but the guy that we're bioengineering might be able to do something like this, right? Might be able to do something like this. So over time, what's going to happen is this guy is going to get competed out and his survivorship curve is going to go away, right? So we kind of have to consider that. I'm not saying that this is definitely what's going to happen, but just kind of use common sense, right? If you're able to survive in very toxic environments, you're going to have much more survivability. Okay, so non-chemical water pollution. After reading this module, you should be able to identify sources of solid waste, and this is going to just be like trash, things that are not chemically dangerous, but still have harmful effects on ocean flora and fauna, right? Explain the harmful side effects of sediment pollution, right? So all the erosion and runoff we've been studying in previous chapters, let's look at what that actually does effectively for our animal and plant life, right? What does it do to have a lot of sediment in the water? Okay, consequences of thermal pollution. This is one of the ones that's, I put a little video in here that I want you to see and understand the causes of noise pollution, right? And this isn't just a hippie thing, this is a real thing. So much solid waste is what we'd call garbage and sludge produced by sewage treatment plants. What it's worth noting here is that we're not talking about toxic chemicals. We're looking at things that harm organisms just physically, things that might get inside them. If they try to eat it or they try to breathe it, it'll obstruct their breathing passageways. It'll obstruct ways that they eat. It'll, you've all seen videos of or pictures of turtles with those little plastic rings that go around soda can tops, kind of stuck around them, and it'll actually deform the shell if it gets on them early enough. You need to know about the Great Pacific Garbage Patch that's accumulated because of the gyres, right, the surface water currents. It's dangerous to both marine organisms and people. That's worth noting. And this stuff eventually gets ground down into very fine particles, and it looks like little tiny pieces of plastic sand, right? You can actually see this in the fossil records and the layers, the different soil horizons over time as the deposition of plastics occur. I think I've mentioned this before. It's called the Anthropocene era. You can actually see the plastic, right? So this happens especially, I know it's kind of hard to see here, but this problem remains in many developing nations as they become more industrialized. They produce more things for people. They start using plastics. They start using more materials for commercial use, and that stuff gets thrown out if they don't have good infrastructure to deal with solid waste. All right, sediment pollution consists of soil particles that are carried downstream, and what this does, when we have things like erosion that come from building roadways, from building buildings and urban centers where people are going to live, whenever we clear out the trees, those roots, we know what roots do. The roots like to anchor down the soil, and when you get rid of the roots, it goes down into the streams and inevitably finds its way into some sort of stream through erosion, weathering, right, through wind or water, right? And what happens is going to happen there with the sedimentation is those soil particles for a while will be suspended, right? And it can make the water, the aquatic biome, brown and cloudy, right? And that's particularly a problem if you have plants on the bottom. You have plants on the bottom, right? So look here. So let's say you have some plants on the bottom, and they're used to maybe an aquatic environment that looks like this. You got the sun, and those sunlight beams can come right down to it, right? But what happens if you mucky up the water? If you muddy up the water a little bit, right? What's going to happen here? If you muddy up the water, well, that's not it. All right, so if you muddy up the water, now all of a sudden, this sunlight might not be able to get through, right? So what's going to happen is that these plants were used to getting some percentage of sunlight all the way to the bottom, but now it's cloudy, they will die, right? They'll die. But then the other secondary thing you have to worry about is fish, right? Fish, they breathe in usually water that they're accustomed to. They've developed with the ecosystem. So if they're breathing in water that's now all muckied up with soil particulates coming in from industrialization and building urban centers, it can block their breathing pathways and they can die. All right, now let's talk a little bit about thermal pollution. I'm going to show you some videos here that some of your classmates did. This is some of the experiments they did with dissolved oxygen. And what happens with thermal pollution is it has to do with things, again, that are non-chemical, just like garbage. Garbage is a non-chemical factor that affects aquatic life and affects biomes. The water pollution occurs when human activities cause substantial change in temperature of water, and this usually has to do with power plants, right? So no matter what type of power plant it is, power plants, right? Well, these power plants, what they do is they usually turn some sort of turbine to spin a generator and generate a current, right? We all know this from when we talked about the last couple of FRQs. But what will end up happening is that water that's turned into steam, right? They use the steam to turn the turbine. will eventually have to be cooled down and re-released back to where they got it. Now, if your power plant's on a river, a stream, or a lake, that hot water is just going to get pumped back out unless people have thought about the effects of thermal pollution and thermal shock, right? You can use cooling towers, right? That's what nuclear power plants do, those really large towers that people think like nuclear gas is coming out of. It's actually not nuclear gas. That stuff is just steam. It's a steam outlet, right? Okay. Or you can use large, long pipes that will let the water cool down for a longer distance before it gets to back into the pond or the river or the stream. Or you can actually have reservoirs of water that are just going to sit and cool before they're discharged back out. All right. And so your classmates came in for a little bit of extra training, and what they were doing is they were doing a dissolved oxygen titration, right? So
Why is this still
So they were getting a baseline comparison of the amount of dissolved oxygen in parts per million at basically room temperature, what the aquarium was at. And what they did is they, let's see if I can get a good one here. Same thing. Okay, so they took the dissolved oxygen there, and they ended up getting about 7.5, right? So that was pretty neat. Okay, then here you can kind of see this was a titration reaction, right? So we're looking for the minimum amount to get it to go back to clear. So you don't have like excess reagents in there.
Two drops at a time and then stare.
See how it's like lightening up. In fact, hold it up to like get it out of your blood so you don't see blue. So what's that look like to you? Purple still?
the top?
Yeah, purple.
See how it's like a purple tinge still? So that purple tinge tells you that there's still some dissolved oxygen that is not combined with the stuff, the indicator here, right? So at the point when this completely turns colorless, that means you've used just the right amount of this titration liquid here to make it completely neutralize, right? And that'll tell you, there's like a little meter here that'll tell you the number of dissolved oxygen that there must be in the test chamber, right? And it ended up coming out to about 7.5, right? So now you look here, when we heated up the water for a little while, let's see if I can move this out the way. We heated up the water for a bit. This was the last trial. So you can see there, that's about 30 degrees Celsius. Now the water isn't hot, but what it's happening is it's taking advantage of the lower boiling point of the oxygen, right? So it's boiling out of the water before the water boils out, obviously, right? So look what's going to happen here. We would count the number of breaths the fish would take, and it started out around 18 breaths in 10 seconds. And look at this last trial, we weren't even able to get a count because look at what the fish did, right? It was very erratic.
I guess go.
His behavior is erratic, right? To say the least, as the temperature went up. Okay.
What? Oh, how much is the fish?
Go.
Okay, so you can see there that he did not like that very much. Now, he did survive. It was fine. We put him back in the tank and everything. We didn't have it very, very high to where he would, boil or anything like that. But he definitely was a little bit in a bit of discomfort, right? And now that was just a difference between 7.5 and 6, right? So just a little under 1.5 parts per million made that big of a difference. Now, if you think about Avogadro's number, that's 6.06 or 6.23 or something like that, times 10 to the 23rd molecules per mole, right? So if you think about that number and how many atoms there are in a mole of water, and then you compare that to how many parts per million would be oxygen, and remember, million's only like 10 to the 6th, right? So that would be quite a few molecules of O2, right? So that's something to kind of consider. So by boiling the water, or making it a little hotter, even though you're not making the water considerably hotter, you are boiling out the gases that the fish need to breathe. All right, noise pollution affects animals. It can mess with their motion hunting, right? Things like submarines and ships. It's worth noting that the Navy is exempt from any noise laws that international laws have kind of come up with to try to protect marine life from noise pollution, right? So you can listen to a video of how the whales kind of hunt and sound versus how it sounds when air guns go off underwater, propellers, right? So these are some kind of things that people do. They make quieter propellers, right? They do ship design to kind of get rid of this, right? All right, now let's go ahead and talk about what we do about some of the things that are causing negative effects on aquatic biomes and animals in them. These are some of the water pollution laws, right? We're going to talk about the Clean Water Act and the Safe Drinking Water Act. We're going to look at how pollution legislation is changing in developing countries, right? Because as we discussed before, the developing countries, sometimes they grow up all at once, right? Things that took us maybe 50 to 80 years to develop the technologies to produce are available right now to developing countries that are industrializing, right? They don't have to discover and reinvent the wheel. Like, there are things out there, right? Like, I don't need to know if I'm, some weird country Zebulon in the Pacific Ocean, right? It doesn't really exist, but I don't need to discover and invent coal and fire up a coal plant and everything. I don't need to learn how to develop that, right? I can just steal that technology or borrow that technology from another country that I deal with. So because the technology is readily available to anybody that wants to industrialize, if they have the means, they have the money, they end up with a lot of the pollution problems all at once, right? And it can have very acute short-term effects, right? Clean Water Act protects water bodies, right? So it's important to know that it's groundwater, right? Supports the protection and propagation of fish, shellfish, wildlife, and recreation in or on the water. Okay, and what it does is it maintains when necessary and it restores chemical, physical, and biological properties of surface water. So that is the goal of the Clean Water Act. Okay. It has the acceptable limits of pollutants in U.S. waterways, and that has to do with all the pollutants that we learned about in 14A, right? What's important to note about this is that it does not deal with things like aquifers, right? This only has to deal with surface water, surface H2O only, right? Okay, not groundwater. Okay, the Safe Drinking Water Act legislation sets the national standards for safe drinking water. And so right now, if you go and look at the video, all the things wrong with Flint's water in 3 minutes, you should definitely look at that, right? Because you should compare what this is supposed to protect, the maximum contaminant level, MCL, for 77 different elements or substances in surface and groundwater. So this one does protect groundwater. But it's worth noting that the acceptable amount of lead you should have in the water is 0. We shouldn't have any. Even very small amounts can have adverse effects on your body, right? Especially neurological things, right? So if we go and look at case studies like things in Indiana and in Flint, Michigan, you can see that the Safe Drinking Water Act might be there, but if they're not being enforced, if these laws on the books are not being enforced, then you can end up with adverse health effects. And so what is the maximum contaminant level? It's the standard for safe drinking water established by the EPA under the Safe Drinking Water Act. So you need to know that MCL is part of the Safe Drinking Water Act. Okay, a couple more slides. Let's look at the maximum contaminant level that we allow. And I would definitely know the ones that are at 0, right? These are the parts per billion. Remember that this is an indicator. This is a contaminant indicator right here, the fecal coliform. You should have 0 parts per billion in that. But this is an easy thing. This is very, very easy to safeguard your water against, right? This is easy. So guess what? If you have even a small amount of fecal coliform in your water, and it's easy to get rid of, then you know that it's probably worth testing for some of these other things, right? Because if this is easy, and we can't deal with it, then it's probably all this stuff's going to happen too. So Giardia, we shouldn't have any of that in there. It's another microorganism. Benzene, only 5 parts per billion. Mercury, 2 parts per billion. Arsenic, 10 parts per billion. And it's worth noting that the EPA and other environmental agencies wanted this down to 5. But this was kind of a happy medium from 50 parts per billion was the level back in the day, and they wanted it down to 5, but they were able to get it down to 10 at least, right? So this will still have some adverse health effects, but it's better than before. Okay, atrazine, we know, is kind of like it's related to plastic, and it has to do with factory production and things like that. And we saw in the documentary Strange Days on Planet Earth that atrazine does have very similar effects to hormonal things like estrogens, right? And that can, in small amounts rather than large amounts, because this bucks the trend, in very small levels, small doses, it has effects on reproductive systems of animals. All right, the Safe Drinking Water Act, the current leading causes of sources impaired waterways in the United States. You made a chart over this, hopefully, but if not, you need to do it now, okay? Streams and rivers, so what are the things that get in there? Bacterial pathogens, habitat alteration, oxygen depletion, and this comes from just not having clean infrastructure to do this. This is runoff, right? Runoff from habitat destruction, building roads. Oxygen depletion could be from thermal pollution, right? But it could also be from eutrophication, right, or pollution. Those things that run into the waterways are synthesized by microorganisms, and they they consume oxygen to carry out their life functions, right? And what is the source of the impairment? We get agriculture, right? We can have runoff and get poop in the water. We can also have eutrophication from fertilizers. Water diversions, dam construction can remove trees and put more water where it shouldn't be, causing a lot of runoff, right? Can also deplete oxygen from somewhere that you had running water. Okay, lakes, ponds, and reservoirs. So how do these things get jacked up? Mercury, PCBs, and nutrients. And that comes from atmospheric deposition and agriculture. Atmospheric deposition is just things like acid rain, right? Bays and estuaries. So we're talking about ocean to freshwater transitions. Bacterial pathogens from wastewater not being treated before it's flushed out. Remember that if we have old wastewater treatment facilities and there's a storm, they are allowed to dump all that stuff out, right? That's the one time it's legal to dump untreated water. So you can end up with bacterial pathogens, oxygen depletion, and mercury from sulfur burning and sulfur production. Or, I'm sorry, not sulfur production, coal production. Okay, atmospheric deposition, municipal discharges, including sewage. Okay, slide here. Water pollution legislation is becoming more common in the developing world. Developing countries have addressed the problems of pollution by cleaning up polluted areas and passing legislation to prevent pollution in the future. Developing countries are still in the process of industrializing and are less able to afford water quality improvements, right? So they're interested in making money, right? They got to make money to get their people fed because the standard of living is going up. So remember we said as affluency goes up, the cost goes up too, right? So what do? Is they're going to increase their industry, right? Right, but increasing your industry usually does what? Increases pollution. Right, so this will happen really, really quickly because we know that the available technologies for industrialization are great, right? They're not having to wait hundreds of years like we had to in a lot of our countries, right? They're going to go through all those growing pains all at once. Developing countries suffer from the additional pollution, but also benefit economically from additional jobs and industrial spending. So they also have the potential to quickly fix their problems, right? And if they incorporate clean, green technologies or renewable energy sources, there's a chance that they don't need to make a lot of the same mistakes that we do. Of course, those things are expensive, so we kind of have to decide as a species what we do about developing countries, right? Do we help them out? Do we help subsidize technologies a little bit because we know that in the long run it benefits us all to not have polluted waters, right? Because we know that a polluted stream doesn't stay in the place that it's polluted, right? That point source pollution doesn't just stay at the point of pollution, right? You end up with this non-point source pollution that ends up running down into everywhere else that gets that water. So remember that even something that does not affect us directly in the short term may have ecological, human, and economic costs in the long run, right? In developing countries, a nation becomes more affluent and it has the ability to I can't read any of this because it cut it off, but it has the ability to develop ways to abate some of this pollution, right? So those are the things you need to know. All right, I hope this was helpful. Take notes on these, watch the rest of the videos. Bye-bye.